researchers have developed a new drug they hope will lower cholesterol. Let's call it T-testrol. They take two groups of people and give the drug to one group for a month. That's the treatment condition. The other group gets an empty pill. That's the control or placebo condition. After that month has gone by, the researchers measure cholesterol for both groups. They find that the control group, which didn't receive the drug, now has a mean cholesterol score of 36. The treatment group, which did receive the drug, now has a mean cholesterol score of 34. Descriptively, these two means are different. But does the drug actually work, or was this just chance? Would a similar result happen again with a new sample? That's why we need inferential and not just descriptive stats. The t-test will tell us how likely this difference is to be reliable, or whether it's just due to chance. Well, how does the t-test do this? How does it work? Well, I won't go into the full formula, but basically it measures the difference between the groups and compares it to the difference within the groups. The t-value is just a ratio of these two numbers, variance between groups over variance within groups. A t-value of 3 means your two groups are about 3 times as different from each other as they are within each other. That also means that if groups have wider, more scattered scores, it will be harder to detect a real difference between the groups than if they had narrow, tightly clustered scores. You can think of it as a signal-to-noise ratio. The signal, that's the difference, is easier to detect when there's less noise. That's the scatter. In our example with the cholesterol drug, the difference between groups is about 2, while the difference within the groups is about 6. 2 over 6 gives us a t-value of 1/3, which is not big enough to be reliable. Based on these results, we can't say the drug actually helps lower cholesterol. But how do we know if it's big enough? Each t-value has a corresponding p-value. The p-value is the probability that the pattern produced by our data could be produced by random data. In other words, it tells us whether the difference between our groups is real or if it's just a fluke. So, a p-value of 0.05 means there's only a 5% chance we would get these results with random data. A p-value of 0.01 means there's only a 1% chance we would get these results with random data, while 0.1 means there's a 10% chance. In most research, the cutoff for what we consider reliable or statistically significant is a p-value of 0.05 or below. The exact p-value associated with a t-value depends on how many people are in your sample. Bigger samples make it easier to find statistically significant differences. For example, with two groups of 5, a t-value of 2 has a p-value of 0.04. When you increase the sample size to two groups of 10, that same t-value of 2 now has a p-value of 0.03. Bigger samples are helpful, but the benefit diminishes as the sample size increases. A good guideline is to try and have at least 20 to 30 data points in each group. If your sample is too small, you may not have the statistical power to detect differences that really are there. Sample size is represented through a number called the degrees of freedom. For t-tests, the df is the sample size minus 1. There are 3 main types of t-test: the independent samples, paired samples, and the one-sample test. The most common type is the independent